Hello everyone and welcome back. Today we'll be doing section 3.3 on the rectangular coordinate system and plotting. The rectangular coordinate system and plotting. So the idea here is that we have some type of equation in two variables. In this section, we're going to restrict those types of equations to also being functions. So remember the work we did earlier in the chapter on functions. So every input has exactly one output. We don't have any inputs that have two or more outputs. The rectangular coordinate system also sometimes gets referred to as the Cartesian plane. Those are both referring to the same thing. And basically all it is two number lines that meet at a nice, neat, pretty 90-degree angle. Now, if you don't have graph paper at home, I know we're all trapped inside for the moment, just a little ruler will do just fine. And I find it's sort of easiest to sketch on the 1/4 inch mark. That lets you have sort of enough points up and down to get a good idea of what your graph should look like. So every 1/4 inch I'll just draw a little hash mark, and same way down here. And I can do the same thing on my horizontal axis as well. So it is important that these are evenly spaced. The reason being that the graphs that we'll be working with do typically have a distinct recognizable shape as long as the axes are scaled correctly. So generally the horizontal one is for your input variable. Quite often that's the x. It's not always the x. Sometimes times the variable, sometimes the t is used. The vertical number line is your output variable, or dependent variable if you want to call it that. Either a y or sometimes an f of x. But that's the general idea, is these are just two number lines. The place where they meet, we didn't just arbitrarily put them together at any point. We put them together where both the input variable is 0 and the output variable is 0. And that's referred to as the origin. So that's where the two number lines meet up. Positive values on the right for your x number line, your horizontal number line, negative values on the left. And the vertical number line works the way you would expect it. Positive is up, negative is down. So notice that this basically cut the paper into 4 sections. We refer to those as quadrants. So the top right one, where both the input and output are positive, is quadrant 1. And then we work counterclockwise. So quadrant 2, input is negative, output is positive. And these ordered pairs are always input first, then output. So positive, positive in Q1. Input is negative in quadrant 2, but the output is positive since we went up. Quadrant 3, we went to the left of the origin, so the input is a negative. We went down from the origin, so the output is also negative. And finally, quadrant 4, The input, we want to the right, so that is back to being a positive, but our output is negative since we went down. So every single point in this plane can be represented by just two numbers. How far left or right we are is the first number. How far up or down we are is the second number. So for example, if I want this point right here, we're in quadrant 4, so I already know what to expect as far as the signs go. My input variable, positive 1, 2, 3, 4, 5. My output variable, I want down just 1, so I'll represent that with a negative 1. So that's the basic idea of the rectangular coordinate system, also called the Cartesian plane. And basically we're going to be drawing pictures of functions in this Cartesian plane. We're going to, in this chapter, still restrict our domain to the set of integers. And every function that we're going to look at, the graph is going to simply be a list of ordered pairs that make true statements. So let's see, I'll just start a fresh page here. So our first function, we'll do just the basic f of x is x squared. So this is equivalent also to thinking of it as y equals x squared. So again, if you don't have graph paper at home, just use a ruler. And I'll go ahead and put my vertical axis on there. So the 3 is where I'm going to put the middle of my vertical axis. And again, just every 1/4 inch, just a tiny little mark. Doesn't take too long to knock that out. And that lets us have a sufficient number of points that we can get a pretty good picture of our graph. Okay, so then I'll put the 3 in the middle again and go ahead and draw another line 2 inches either side, and we'll just hit a little hash mark every 1/4 inch. You get faster and faster as you do more and more of these. If you do have graph paper at home, that's great. Then really you're just drawing in the axes. Okay, so our vertical axis this time is f of x. Our horizontal axis this time is measuring then just x. So we'll have our domain. That is our x value. Our rule, in this case, our rule is f of x is x squared. And we'll do a little work and get a range value, in this case, f of x, which will let us find an ordered pair. So we'll start simple. We'll start with a 0 for the input. So f of 0 is 0 squared. 0 squared, 0 times 0 is still just 0, range value of 0. So this one does go through the origin. So my first point is on 0, 0, left and right 0, up and down 0. Then I'll try out a positive 1. F of positive 1, positive 1 squared. 1 times 1 is just 1. So 1, 1 is also a point on this graph. So I go input is 1, output is 1. Once I've done both of those moves, then I put my dot. So notice I'm not putting a dot on the x-axis by going to this 1. I'm first just moving to the 1 and then listening to what the y coordinate is telling me to do as well. Well, let's try a negative. If I try negative 1, f of negative 1 is negative 1 quantity squared. So negative 1 times negative 1, which is a positive 1. So I put an input of negative 1, got an output of +1. So starting at the origin, the -1 tells me to go left 1. Then the +1 in the output part of the ordered pair tells me to go up 1, and I'll put a dot there. So then we'll go to an input of 2. So f of 2, 2 squared, which is +4. So 2, 4 is also a point on my graph. So at the origin, to the right 2, and then climb up 4. You can probably predict what's going to happen with this -2. -2 quantity squared, negative times a negative, just like before, flips us back over to the positives. So -2, +4 is also a point on our graph. So I'll go left 2 and climb up 1, 2, 3, and 4. If I go to 3, f of 3, 3 squared is +9. So 3, 9 is a point on our graph. So to the right 1, 2, 3, and up 4, 5, 6, 7, 8, and 9. And I'll let you do the math on the -3, but we will indeed get an output of -3, +9. Anytime you see a function that involves an x squared, this is the general shape that you'll see. So it might open up, it might open down, it might be centered on the origin, it might be centered here in Q1, it might be centered down in Q4, but you should expect to see a U shape anytime you see an x squared involved in your function. Now, as far as integer inputs, this is the graph. If you wanted to expand to the real numbers for our domain, which we're not going to at the moment, we would just lightly connect them with a smooth curve and arrows on the end. So this pattern would continue. That's what the arrows are telling us. This pattern keeps going. Okay, so next up, another of our, we call them basic functions. Not basic because they're considered easy, but basic because I only have one thing happening to them at a time for the moment. So g of x is the square root of x. So again, I'll go ahead and get this graph centered on the 3. Draw a nice vertical line there, and our little hash marks every 1/4 inch. Again, if you have graph paper, that process is a little bit shorter. And then we'll go ahead and rotate and do the horizontal axis as well. And hash marks every 1/4. So this time my vertical axis is the g of x axis. The input is just x. Now in this one, we do have to be a little bit more careful with the points that we select for our input. So our domain here, domain values are x values. Our rule for this one, g of x, is square root of x. And our range values, those are our g of x values, quote unquote y. And then we have our ordered pairs. So again, I'll start with the basic 0. G of 0, square root of 0. So that's asking the question, what number can you multiply 2 copies of to reach what's underneath? Well, 0 squared will give me a 0, so our range value is 0. So this one too, I'll start at the origin. So where the two axes meet. Axis is singular, axes is plural. Okay, so then we'll go over to 1. G of 1, square root of 1. Again, it's asking the question, what can I multiply 2 copies of to reach 1? Well, 1 times 1 will give me a 1 back. So we also have 1, 1. Negative 1, however, g of negative 1, square root of negative 1. Now it's asking me to multiply 2 copies of something and get a negative. Well, a positive times a positive is a positive. A negative times a negative is a positive. And 0 times 0 is just 0. This one can't be done in the real numbers. So there's not going to be an ordered pair for negative 1 or negative anything for that matter on this one. I need the stuff under the radical, the radicand, they call it, to be 0 or a positive. 2 presents kind of a similar problem. Square root of 2 is not a nice, neat, pretty rational number. Remember, that was in our set of irrationals, set T. So the next perfect square that I have, I'd have to go all the way to 4. So g of 4, square root of 4 is just a nice, neat, pretty 2. So 4, 2 is the next ordered pair that would be on this. So from the origin to the right, 1, 2, 3, and 4, and up 1, 2. Next perfect square after that, I've got to go all the way to 9 to get there. G of 9, square root of 9, which is just a 3. So 9, 3 is my next ordered pair. So to the right, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and up 1, 2, and 3. So this time, again, the points themselves are the integer, domain, and range. The thin curve connecting them is just showing the pattern. And this is also going to hold. Anytime you see the square root in the original, you're going to have this basic shape. Again, maybe it's flipped upside down, maybe it's opening to the left instead of to the right, maybe it's moved around, but you'll have this basic shape happening. All right, so our next basic function is our friend, the absolute value. Let's see, we already used f and g, so this guy is going to be h. So h of x, again, I'll use just the basic, only one thing happening, absolute value of x. Our domain, our x values, our rule. H of x is absolute value of x, which will spit out a range value. In this case, our range is h of x, which will lead us to our ordered pair. So if we start with 0, h of 0 is absolute value of 0, absolute value of 0 is 0. So this one too, we have the origin. So then we'll try out our, make sure that 3 is lined up nice. There we go. Here's our 3. So while I'm working on this, I would suggest trying out a 1 and a negative 1 and look for a pattern. So our vertical this time is h of x, horizontal is x. So you may have noticed some similarity between how this one started and how our friend the quadratic started, the x squared guy. You should have found that we have the same 3 first points as we had on the x squared graph. So clearly 3 points is definitely not going to be sufficient for our work with nonlinear functions. So h of 1, absolute value of 1, which is just 1, range value 1, so we have 1, 1. Absolute value of negative 1 is positive 1, so we have negative 1, 1. So far, the first 3 dots look the same as they did back in our square function days. But as I keep going, if I try out a 2, h of 2, absolute value of 2 is 2. We get 2, 2. So where our square went up quite a bit, this one went up just 1 again. Absolute value of negative 2 is still a 2. So negative 2 for an input gives you 2 for an output. And that should keep happening. Absolute value of 3 is 3. Absolute value of 4 is 4. Absolute value of 5 is 5. Absolute value of 6 is 6, and so on. Absolute value of negative 3 is 3. Absolute value of negative 4 is 4. Absolute value of negative 5 is 5, and so on that way. So notice these line up to a nice, neat, pretty array going that way, and another nice, neat, pretty array going this way. Absolute value, you will see a V shape. So if you're working on an absolute value problem and you only see a line, keep looking, keep plotting more points until you find where that bounce is. So some of them might look linear at first. All that means is you've got to keep moving around, keep trying other domain values until you find where the graph turns around. Okay, so we've played with square functions, and we've solved those when they were one variables by just factoring. Our square root ones, we isolated the square root and solved that way. Absolute value, same idea, isolate the absolute value and solve from there. One other type of equation that we've worked on that was nonlinear was the rational. So the rational one, we'll play with this one. Let's see, I don't want to use j. So j of x, for us it'll be 8 over, let's say x minus 1. So like our square root equation, we have to be a little bit more careful with our inputs when we have a rational equation. But the ideas are still the same. We're looking at domain values. In this case, we stuck with x, some kind of rule connecting them. In this case, g of x is 8 divided by the quantity x minus 1, which give us our range values. Range in this case being j of x, and we make our ordered pairs from those. So right away, there's one value that I definitely have to stay off of. Remember, we're never allowed to divide by 0. If I plug in a 1 for the x, I get a 0 at the bottom. So positive 1 is not going to be in my domain. So x cannot equal a positive 1. So what I'll do is just kind of move out from there then. So we'll try maybe a 0 to start us off. So j of 0, 8 divided by 0 minus 1, which is 8 divided by negative 1, which gives us a range value of negative 8, and an ordered pair 0, negative 8. So moving to the other side of 1, we'll try out a 2. So j of 2, 8 divided by 2 minus 1, which is 8 divided by positive 1, which is a positive 8. So 2 and positive 8. Now with this numerator of 8, and us looking to keep with nice, neat, pretty integer answers, I want my denominator to be something that is a factor of 8. Well, 1 is a factor of 8. 2 is also a factor of 8. So if I try out a 3, j of 3, 8 divided by 3 minus 1 is 8 divided by, there's that 2 we were hoping to find, 4. So 3, 4 is on there. So let's see, that was 2 units to the right of our excluded value. Now I'll move 2 units to the left of my excluded value, which takes us to a -1. J of -1, 8 divided by -1 minus 1 is 8 divided by -2, which is a -4. 3 is not a factor of 8, so I'm going to skip over the 3 and concentrate on what I would do to get a 4 at the bottom there. I would have to plug in a 5. 5 minus 1 will give me a 4. So j of 5, 8 divided by 5 minus 1 is 8 divided by 4, which spits out a nice, neat, pretty integer of 2. So 5, 2 is on our graph. Let's see, so that's 4 units to the right of our excluded value, so I'll move 4 units to the left. That will take us to a -3. J of -3, 8 divided by -3 minus 1 is 8 divided by -4, which is a -2, so -3, -2 is also on our graph. So after 4, 8 is the next multiple of, or I'm sorry, not multiple, factor of 8. So I'd have to go all the way to 9 to get that job done. So j of 9, 8 divided by 9 minus 1, which is 8 divided by 8, which is a nice, neat, pretty 1. So 9, 1 is on my graph, and let's see, so that moved us 8 units that way, so 8 units the other way would be -7. J of -7, 8 divided by -7 minus 1, 8 divided by -8 is a -1. So -7, -1. Okay, so with the fraction, that ate up a fair amount of our room here. So we'll kind of flip back and forth. Let's leave this one page blank so we can flip a little more quickly. Okay, so I'll get my 3-inch mark centered on there. And our 1/4-inch marks here. Okay, so here we go. That's there. And our scale on the horizontal axis as well. Okay, so our input was an x, our output was j of x. So plotting our ordered pairs, we have 0, -8, and 2, +8. So left and right 0, down 8. 1, 2, 3, 4, 5, 6, 7, and 8 down. And we had 2 and +8. So right 2 and up 1, 2, 3, 4, 5, 6, 7, and 8. 3, 4 was up next. So from the origin, right 1, 2, 3, and then up 1, 2, 3, and 4. Then we had -1, -4, left 1, down 1, 2, 3, and 4. 5, 2 was next up. To the right, 1, 2, 3, 4, and 5, and up 2 units. -3, -2 next. So from the origin, left 1, 2, 3, down 1, 2 for the -2 in the output position. 9, 1 to the right, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and up 1, and -7, -1, left 1, 2, 3, 4, 5, 6, 7, and down 1. So on this, really, you may notice we have sort of two separate patterns happening, and then we have at -1, we had no values at all. -1 would force us to divide by 0. So this one, we have sort of two pieces to the puzzle. Now, this is not to say that every single rational equation, every single fraction involved equation will look like this. This is just kind of one of the more common shapes when it's a constant over a first power variable. But on this one, the shapes can vary. Okay, so that should give you enough practice to go through the problems at the end of section 3.3. So again, that is 3.3. Please feel free to get in touch with me with any questions you might have. If you want to check over your work, anything like that, feel free to get in touch. Stay safe out there. Hope your families are safe as well, and I will see you next time.